have any doubt about it when I go over this section. Okay, so far we know how to integrate. We can integrate the double integral and the triple integrals. Okay, so we have all the information that we have. So as we did it with the double integral, there are some type of functions that's going to be sometimes impossible to do it with a rectangular coordinate, so we switch. In the case of the double integral, we switch into the polar form. Okay, now what we're going to do in the case of the triple integrals, you have two choices. One choice going through the so-called cylindrical coordinates, and the other is going to be going through the spherical coordinate. The name are coming because these two, the cross section or the section that the three-dimensional solids that are going to be involved. For the first one is going to be cylinder, and the other one is going to be a sphere. Make things so easy for us, and there are some integral that without this type of techniques you can't do it. On the test, we directly give you the instruction to do a cylindrical or to do the spherical one, and sometimes we may not mention anything. Then you will find it, you just do it yourself. Okay, so there you are. So we do the 14.7. Okay, so briefly, we have to remind ourselves regarding cylindrical coordinates. We don't need match, so that's why we didn't cover it before. So whatever we need, we are going to see it here. Okay, so first we have to know what is cylindrical coordinates. Okay, cylindrical coordinates. It would be polar coordinates in three-dimensional. Remember the polar coordinate, you change the x and the y into the r and the data. And you know a relationship between these two. So if you fix the z as is, you see, this is z as is, but in two-dimensional for the x and the y, you change your x and the y into the polar coordinate. So your x would be changed into the r, remember, x and the y would be changed to the r and the data. Then you keep the z. So your cylindrical coordinate would be r, data, z. So if you forget about the z, the rest you are in two-dimensional. Means the projection of that three-dimensional solids that are going to have in the xy coordinate would be in polar form. Okay, that's the general idea. Now I'm going to explain it for you. This is going to be the one that we are going to use. Okay, so there you are in cylindrical one. In cylindrical coordinates, we replace x and y. We replace x and y coordinates. Okay, coordinates. Let's see, of a given point, of a point P, which is given by x, y, z in rectangular coordinate, now bipolar. Okay, bipolar coordinates, polar coordinates of of P. So the polar coordinate, of course, will be this part that we're going to have. Now the cylindrical coordinate. Now the cylindrical coordinates of a point of P are going to be, you see, are going to be R, data, and Z. So we keep the Z. But this is going to be the case where if you forget about the Z, this part is just the polar coordinate of X and the Y. So the projection is going to be polar coordinate, okay? Where R and data are going to be our polar okay, are polar coordinates of x comma y. Okay, so this is going to be the idea that we're going to have. So this is what will happen if you consider the x, y, z. Okay, if you consider this one, for example, to be your x, y, z coordinates. So remember, you start with your point. Your point is going to be x and y. You see, this is going to be your x. You know that this is going to be your x. You get, you get this part to get to the, okay, to get to your y, to get your y here, and then z up. Okay, so this is going to be z up, and this is going to be the point, which is going to be x, okay, y, z. Now, the thing that would happen here, you know that this point, this is going to be the point q, for example. In two-dimensional, this is going to be x, y, and 0. So what we do, we change this one into the polar coordinate. So for the polar coordinate, you are going to get something like this is going to be, okay, this is going to be your data. Okay, this is going to be your data, and you are going to be in two-dimensional. So in fact, this q would be changed into the r data and 0. And we know the relationship, this x would be r cosine of the data, and then y would be r sine of the data. That's a relationship that we have. Then the point eventually, this is x, y, z, then would be changed into the, okay, would be changed into the r data and z. Okay, this is the way you look into it. So the projection into the two-dimensional is going to be just a polar coordinate, and the z is just going to be a fixed one. Okay, now how we go from one side to the other side, do the conversion, if you like, of these, that we are going to need them. Okay, the conversion is going to be in this form. So if you have a rectangular, okay, if you have a rectangular, coordinate, and your point is going to be x, y, z. And if you want to change this one into the cylindrical one, and this is going to be cylindrical coordinates. So you are going to change it to the r data and z. Now the question is going to, how are we going to find these? You are going to find them from your polar case. So you have the x and the y, you know that you are going to find the r by this equation, x squared plus y squared. And if you want to find your data, you go with the formula that tangent of the data is equal to the y over x. And that would imply that the data is going to be tangent inverse of y over x. Okay, so if the x, y, z coordinate would be given to you, this is the way you're going to change it to the cylindrical coordinate, and using that formula. Okay, the other way around, if you have a cylindrical one, you usually have the first one, cylindrical coordinates. So in that case, you are given an r, you have the r and the data and z. This is the way you're going to be given, and you are going to read it. So from this side, if you want to change it to the rectangular coordinate, okay, rectangular coordinates. So your rectangular coordinate is going to be x, y, z. Okay, your z is constant, your z is fixed. So z is z, but if you want to find the x, so your x going to be calculated from this one, r cosine of the data, and y from the fact that there is r sine of the data. Okay, so this is the way we go across these two coordinate systems. The function part is the part that we are going to convert, and we needed that to get the idea. So I'll give you a couple of examples because we haven't done it before, just to get to know them. And when it's given to you, but your job is just the integral part. Okay, any question? So I'm going to give you one from each coordinate system going to the other one and coming back. And so you know how to pick those because there are going to be limit of integrations in future. Okay, so let's get a couple of them. Of course, we are not going to question you this conversion one because you do it automatically for us in the problem that we are going to be having. Okay, so let's take one from each. So for example, convert. Suppose you want to convert R, data, and Z. So it's in cylindrical coordinate and it's given to you as 2 pi third and the 5. So you want to convert this one to the rectangular coordinates, okay? To rectangular coordinate, rectangular coordinates of this form, X, Y, Z. Okay, so that's easy because R and the data is given to you. You want just to convert it. So you just note that your given information are going to be your R is equal to 2. Your data is given to you is equal to the 2 pi third. And you already got the Z. Z is equal to the 5. So you already got the Z. So you need to find the X and the Y. So you know that it's polar coordinate. So in polar coordinate, X would be R cosine of data. R is equal to 2 is the cosine of the 2 pi third. It's a cosine of the 120. So from the unit chart, it's 2 times the negative half, which is going to be -1. Okay, so X coordinate is going to be -1. And we do the Y coordinate, it's going to be Y equal to the R sine of the data. So there's going to be 2 sine of the 2 pi third, sine of the 2 pi third in the 2-dimensional. In the second quadrant would be radical 3 half. So it's going to be 2 times radical 3 half. So that gives you radical 3. So your Y coordinate is radical 3. Okay, so there you are in the X, Y, Z coordinate. The point would be represented by X is a -1, Y is a radical 3, and Z is 5. Okay, so this is going to be the one. Okay, any question? So not big deal, but get the feeling, you know, that you are in new environment, if you like, new system, and know how you're using, you know, these notations. So give me one more, the other way around. This next one, you got to be careful as you did with the polar coordinate. So the other way around is you want to convert from a rectangular coordinate. So convert. Okay, you convert X, Y, Z, which is given to you is a negative radical 3. You have the -3 and 5. You want to convert it to the cylindrical coordinate, okay, to cylindrical coordinates of the form of the R, data, and Z. Okay, again, collect your information that you have and change it to what you are looking for. So the information given to in terms of the rectangular coordinate, so you got the X equal to the -3 radical 3. Okay, Y is equal to the -3 and Z is equal to 5. So again, the Z is going to be fixed. So you already got the Z. So you need to find the R and the data is in the polar form. So you need the R. So your R is going to be a square root of X squared plus Y squared. Okay, you substitute. So that gives you negative radical 3 squared plus -3 squared. So this would be what is radical 3 squared would be 3, and the 9, 27. Okay, 27 and the 9, which is a radical 36, which is equal to the 6. Okay, so R is equal to the 6. Okay, now to pick the data as you have it with the polar coordinate, you got to be careful. You check to see in two-dimensional in which quadrant are going to be, because you have to pick one data only. We know that there are infinitely many solutions. So you just identify the, to find the data. So identify the position in two-dimensional to see in which quadrant are going to be. So X and the Y, both of them are negative. So you are here. So your data is going to be this one. Okay, so that will help you to pick the correct one because of the tangent that you're going to use. So this is the only thing that you got to be careful. So the tangent of the data is going to be y over x. Okay, y over x, and in this case, the y is a -3, and the x is negative radical 3. So if you simplify that, give 1 over radical 3, which is going to be radical 3 over 3, the tangent. You know the tangent is positive, it's going to be positive in the first quadrant and the third one. And you know that you are going to be on the third one. So if, since you are in the third one, radical 3 over 3 is the tangent of the 30 degrees. But since you are in the third, so it's going to be 30 plus 180, which is going to be 210. So the data is going to be 210 or 7 pi 6. So you got to be careful, to pick the correct numbers. Okay, because you just identify x and the y are both negative. So you are on the third quadrant. So this is going to be your data. It's not going to be radical 3 as a, okay, here as a 30 degrees. Okay, again, not big deal. So we are ready so that in the case of the R data and Z, your points are going to be your R is equal to the 6 and the 7 pi 6, and the Z is fixed, which is equal to the 5. Okay, so this is to get to know this system. Any question? Important part for us is converting the equations, because this is the equation that we're going to handle when we get to the integral. Okay, you have some. So in the case of the in the case of the polar coordinates, for example, the equation is what? R equal to the f of data. We define the R in terms of the data. In terms of the cylindrical coordinate, you have the R data and Z. So the equation that we are going to be interested in are going to be the Z in terms of the R and the data. So I just give you a couple of them, famous one that we're going to use to know what does it mean when we say converted in future, okay, or in minutes. Any question? So let's get this a couple of famous equation that we're going to change. So this is the case. This is important for us to know this, okay? Otherwise, the rest are just coming. Those limit of integration is going to be given to you. Okay, so we check a couple of them if we would like you to find. Okay, that's the idea. Find, and you do it automatically yourself. And that's it. Find an equation. Okay, find an equation. We'd like to find an equation of the form. Okay, this form, z equal to f of r comma data. So you solve z for r and data. That's the type of equation of it. So find an equation of the form. So for given, of course, surfaces that you are going to use. The surface is going to be z, is going to be a function of x and the y. The most popular one, of course, is the first one. So it's x squared plus y squared plus z squared equal to the 9. You know that it's going to be a sphere. So if you happen to use it for integration, and you may have to convert it to the cylindrical coordinate, that's it. You have to solve a kind of for z to to change it. And the way we do it, we just substitute those type that we have. You keep the z and you substitute for the x and the y. Okay, so the solution is going to be, so you substitute x equal to the r cosine of the data and the y equal to the r sine of the data. You know that z is going to be just the z. You keep the z as is if you like. So we put it over here. So this is it. It's going to be x squared. It's going to be r squared cosine square of the data. And this is going to be r squared sine of the data. And you keep the z squared equal to the data. Try to simplify it if you can. You put out the r squared, sine squared, cosine squared would be 1. Okay, so this is going to be r squared. So we are going to have the r squared plus z squared equal to the, okay, is equal to the 9. So you solve for the z squared would be 9 minus r squared. You take the square root, z would be positive negative, okay, 9 minus r squared. So, if you have extra condition for the z, you may get that just the positive part, but eventually this is the equation I'm going to have. Okay, any question? So we are going to do quite a lot of these type of ideas because the function that are going to be integrated is going to be, the region is going to be kind of a surface involved. Then you have to, when you convert from the rectangular one to the cylindrical one, then you have to convert the function. So that would be needed. So don't be surprised to do this type of things for us. Any question? That's one. The other famous one that we do is plane. Okay, so if you have a plane x plus y plus z equal to 1, and if you want to do cylindrical one, again, you keep the z and you substitute. So for the solution, we just, x would be r cosine of the data, y would be r sine of the data, and you keep the z. So if you substitute, you don't have much to simplify. It's going to be r cosine of the data, and that would be r sine of the data, plus z equal to 1. So simply z equal to the 1 minus r cosine of the data minus r sine of the data. This is the best we can do. Okay, so that gives you the idea. Okay, any question? No. Now we are ready to apply it, of course. Okay, x plus y plus z equal to the 1. So what we are going to do is a triple integral would be given to us in x, y, z. So we know that in two-dimensional, that part of the rectangular one and change it to the polar is the one that we did before. So we have only the z part. So this is going to be the case. So if you keep the z constant, if you keep the z fixed, you fix the z, but x or y, you change it to the polar coordinate. So in that case, you are going to have okay, you have the integral, triple integral in cylindrical coordinates. So you keep the z, then you project your region. Your region is going to be, a solid. So you project it onto xy coordinate on the plane. When you project it to the plane, then you change that plane part into the polar coordinate. And you know that in a polar coordinate, x would be r cosine of the data, y would be r sine of the data, and there is an extra r. Remember the Jacobian that you're going to see it by the end of this week. So officially, this is how are going to change integral or a triple integral into the cylindrical, okay, cylindrical coordinate. So let me write it down, okay. So this is it, triple integral. Okay, triple integrals. Triple integrals in cylindrical coordinate, okay, in cylindrical cylindrical coordinates. You already done the polar one, so you have a good idea of the two-dimensional case. You know, you fix the z, you drop down to the two-dimensional. So there you are. This is the way we do it. So we have a region which is x, y, z. We keep the z. We change the x and the y to the polar form. So the new region is going to be what? It's going to be in three-dimensional in the cylindrical coordinates. So we are going to have r data and z. So this is it. This is how you set it up. Because of the polar coordinate, really, we don't have much to do. For a region, okay, for a region W of the form. You see, this is the way we change it, of the form. Make sure you have enough space to write it down. W is equal to, so into the cylindrical, you get R, data, Z. Okay, the way it's going to be, these two may be between two fixed numbers, but this Z can be a function of R and the data. So this is it. The data is going to be between two numbers. It's just, 0, pi, pi half, etc. So that's going to be the data. Then R, again, two fixed numbers, going to be alpha and beta. But that's the Z part, that this Z can be, it depends on the nature that we have. This Z can be a function. It's going to be can be a number, can be Z2, but maybe a function of R and data. And maybe this is the same thing, Z1, a function of R and data. Okay, so this is going to be our region. It depends which type of region do you have. Remember, like those, we call it type 1, type 2. The same thing over here. So for a region W of this form, now the triple integral, okay, this triple integral, this is it, 1, 2, 3, on W, the function f, x, y, z, dv, now it's going to be equal to, so the cylindrical one is going to be equal to you see, the double integral part is going to be just the polar form. This is from alpha to beta. This is going to be the data 1 to data 2. That's the case. But the next part, z is fixed. It's going to be z1 to z2. z1 to z2. You go to the function. For the x and the y, you're just using the polar coordinate. So it's going to be r cosine of the data. If we need, substitute r sine of the data. Remember, your z is fixed, is unchanged. The extra r, if you like to remember from the polar coordinate, call it Jacobian, and you will see at the end of this chapter why it's going to be happening. So the extra r, because of the polar coordinate that you did have it, okay, and then you integrate respect to the z, respect to the r, and the respect to the data. Okay, this is going to be your case. Now, the important part is, if you forget about this part, this is polar coordinates, and you know everything about it. And that projection into the two-dimensional is the important part of the integral. So it's important to know that and note that. I just break it down or drop it down in two-dimensional. If D is going to be equal to, in polar form, R and data, this means this part. R and data, when data is between data 1 and data 2, and this is data, and R is going to be between alpha and beta. If this is going to be is the projection, is the shadow, the projection is the projection, okay, projection of W in three-dimensional. Now you project it onto XY plane, two-dimensional. Then you can imagine the integral as this, that your triple integral 1, 2, 3, f of x, y, z, okay, dv over W, you can think about it as, you see, these are going to be, as I talked about it, in the polar type, and then in integral of f of x, y, z, just dz. Okay, dz, then the dA. This is a kind of just to, and this is of course the z from z1 to z2. So this means you take care of the z part first. The leftover is going to be polar coordinates. Okay, so this part inside is just integrating respect to the z. So whatever it's given to respect to the z, then the rest you can imagine that it's going to be in polar coordinates. So that will help you quickly to organize it, to set it up this part. You know that what would happen to the data, what's happened to the R, and those symmetric format most of the time, like the one that we did before, would be covered. Okay, so basically cylindrical coordinate is the extension of the polar coordinate. Polar coordinate for the two-dimensional and the cylindrical coordinate for the for the three-dimensional that we're going to have. Okay, so this is going to be the case. Any question? So it's important to be able to operate it, okay, to see how we're going to do it, and it's going to be quite nice one, quite nice integral. You will see sometimes there's going to be a choice between cylindrical and the spherical, and then you will see the role of the cylindrical. It's easier to handle this one. Okay, so let's see. Examples are mostly straightforward. There are a couple of them which is tricky, and you usually may make a mistake. You have all of them in your practice one, on the practice that we're going to have. And of course, they are going to be all parts of your final review. Remember, we're not going to add, we add to it, of course, from the chapter 15, but everything we do so far are going to be repeated. So there you are. Let's check quickly how we're going to do it. We are going to give it instruction, apply the cylindrical coordinates. Of course, these are not going to be possible to do otherwise. There you are. Let's start with this one. Apply a cylindrical. Okay, apply a cylindrical coordinates. Coordinates to evaluate means you have to, okay, to evaluate this integral. Look at the integral 0 to 1, negative 1 to 1, and you have a negative square root of 1 minus y squared to the radical 1 minus y squared. Okay, and the inside you have x squared plus y squared to the 1/2 is a square root. 1/2, and you have the dx, dy, dz. This is what you have for your integrals. Okay. Now you have to get that two-dimensional part that we talk about in the image that we're going to have. So you read this information to identify what would happen in two-dimensional. Your z is always a fixed one, so you don't have much to do about the z. Okay, so read the information, and this is the way you're going to organize it. Solution, are you ready? So read the information carefully. You see, you integrate respect to the x first. So your x is between, so we start with the fact that x is greater than or equal to the negative 1 minus y squared, and this is going to be 1 minus y squared. This is the reading from the first part, then you get the y. So your y is between negative 1 and 1, and your z is between 0 and 1. 0, 1. So you don't have to do anything about the z part because you already got it. Okay, so you have to focus on this. You drop it down into the two-dimensional xy coordinate to see what type of shape are going to have for the polar coordinate. And you know that you start from this part. So we start from the fact that, okay, there you are. So what you have the fact that the x is equal to the positive negative 1 minus y squared. Okay, you square it. So that give you what? That give you x squared equal to the 1 minus y squared. And that give you x squared plus y squared equal to the 1. You know that. Unit circle. Okay, so you get the unit circle from this one. So, so far in two-dimensional, you will end up with a unit circle, which is very easy to handle. Okay, so this is going to be so far. Then you're going to check to see if you are going to use all of them. You know that this is going to be -1 plus all of the place. That's it. And so this is going to be x is between these two. So the semicircle to the right, to the left, all of them are going to be covered. Okay, so you have all of them over here, and then you emphasize it by the given part here. You see your y is between -1 and 1, so you are going to have the full circle in two-dimensional. Okay, so you have a positive negative over here that will tell you both are going to be used. So in two-dimensional, in the two-dimensional, you're just using unit circle, and the unit circle in polar coordinates can be identified by what? R is going to be the radius. So the radius is 1, so R is between 0 and 1. Okay, you're using the full circle. So the data is going to be between 0 and 2 pi. And of course, Z is fixed. C is between 0 and 1. This is going to be the limit of integrations. Any question? Now we quickly change it to the cylindrical coordinates. Okay, so we identify the limit of integrations, the function. The function is x squared plus y squared to the 1/2. Easy to change it. Okay, so easy to change it to the polar form. So r squared, yes, would be r, and then we set it up, and then we're done. Okay, so this is it. I'm going to call this integral I because I don't want to repeat it. So let's try to do it over here. So there you are, I into the cylindrical coordinate. There you are. So I go with the data 0 to 2 pi. I go with the r 0 to 1. Then I go with the 0 with z, which is 0, 1. So if there's going to be any function, you have to change it to the polar coordinates. That's it. X squared plus y squared is r squared. You know that x is r cosine and y is r sine. So it's going to be 1/2. Remember extra r, don't miss it. In the extra r, then you integrate respect to the z first, then you go to the r, then you go with the data. Okay, so this would give you r. So this would be r times r, which is going to be r squared. So we end up with a 0 to 2 pi. Okay, 0 to 1, 0 to 1, and we get the r squared, then the dz, the dr, the d data. Okay, so integrate respect to the r first. Oh, sorry, respect to the z first, which is constant. So that gives you 0 to 2 pi, 0 to 1. So this would simply zr squared, and the z going from 0 to 1. And when we're done, we do the dr and the d data. Okay, if you put z equal to 1, that gives just r squared. So it's going to be 0 to 2 pi, 0 to 1. Okay, r squared, dr, d data. R squared would be r cube over 3. This is going to be 0 to 2 pi. Okay, it's going to be r cube over 3. But r going from 0 to 1. Okay, then the d data. We put the 1, you get a 1/3, 0 is nothing. So it's going to be 0 to 2 pi, 1/3. Okay, 1/3 of the 2 data, which is going to be now 1/3 of the data going from 0 to 2 pi. If you substitute the 2 pi, that gives you 2 pi third. 2 pi third, the final answer. So I would be equal to the 2 pi third, and we're done. Nice integral, see, it's fine. Any question? Of course, you can't do it otherwise, because if you want to do it, you have to integrate with respect to the x to start with. It's not possible. So the cylindrical coordinates is going to be the best method to do, to take care of this one. Okay, so if you set it up, it's nice. The result is mostly, I told you, there's going to be just a couple of them. Otherwise, it's fine. Okay, any question? Let's do quickly one more. The next one is very similar, but there is going to be a difference because in this case, the z was just a fixed number. Okay, z was between 0, 1. So I'm going to give you something else that you will see that you may have to do something to the z too. Okay, so let's get another one of the polar coordinates. So I'm going to call this one number 1. So this is our number 1 example. For the cylindrical one, let's do the number 2. What's the difference between 2 and the 1? Okay, so using cylindrical coordinate, again, integrating this one. Integral from -1 to 1, integral from negative square root of 1 minus x squared to the radical 1 minus x squared. And then this is the difference, you see, it's going to be from 0 to 2 square root of 1 minus x squared minus y squared. And there's no function here, so you're integrating with respect to the z function is 1, like the word. This is your integral. Okay, so quickly check the range of the xyz to see what type of what type of region or domain are going to have. Are you ready? Solution. Rewrite the information that you have. Okay, there you are. This is it. This is x. So your x is between -1 and 1. This is y. So the y is this one. So in the xy coordinate, you have nothing to worry about. This is a semicircle. You have both of them positive, negative. So it's going to be just the same thing. It's a unit circle. But the difference is here. Your z is between, okay, z is greater than or equal to the 0, but it's less than or equal to the 2 square root of 1 minus x squared minus y squared. You see, your z is not a fixed number in this case. So when it's not a fixed number, you know that you have to change it to as a function of r and data, and then you take care of it. Okay, so we know we have to say we start from here to confirm the unit circle into dimensional. So this is it. And you know that you square it, y squared equal to the 1 minus x squared. So you have the unit circle. X squared plus y squared equal to the 1. So that would be easy. This is it, the unit circle. Okay, that's going to be your unit circle, everything inside. Okay, so this means your r would be radius is 1. And since using the full circle, so your data is going to be 0 and 2 pi. Okay, so this is a two-dimensional case when you project it. Any question? You have more job to do for this. Okay, because it's not a fixed number, because you integrate respect to the z first. So it can be, it is in terms of the x and the y. So you have to change it in terms of the r and the data. So we start from this part. We get the z. Z is equal to the 2 square root of 1 minus x minus y squared. Okay, this is going to be your z. So you keep the z, you change this into the r and data. And you know that you can rewrite it as z equal to the 2. And that's going to be 1 minus x squared plus y squared. And x squared plus y squared is r squared. So your z would be 2 square root of 1 minus r squared. So you change the z into the r and the data. So your z, because the other side is 0, so the limit for the z is this one. Okay, 2 square root of 1 minus r squared. So this is how we're going to integrate it. It's a little bit different from the other one because of the z. You have a little bit more work to do rather than the other one that we did. Okay, so set up the integral. We call it I as usual, not to repeat it. So this is going to be the I. So let's see what we have. Then we have a triple integral. That's going to be 1, 2, 3. So if you want to do the data 0 to 2 pi, we do it last. In the middle, we did the r. And we start with the z, which is going to be 0. And that would be 2 square root of 1 minus r squared. Okay, so that's going to be, and there was no function here, but remember the extra r. So when we change it, when you switch it, we have extra r, Jacobian. And then as you did it, you do the dz first, then you do the r and do the data. So this is how you set up your integral. Okay, so this is it. Any question? Integral easy to evaluate. Okay, so the first part at least is easy. You integrate respect to the z. It's a constant, so to give you rz. So let's do it. It's going to be equal to, we have 0 to 2 pi so far, 0 to 1. And that would be rz, but your z going from 0 to 2 radical 1 minus r squared. And when you're done, dr d data. Okay. So when you put z0, we get nothing, but you have that radical to handle. So it's going to be 0 to 2 pi. Okay, 0 to 1. It would be, this is 2 radical. So that gives you 2r radical 1 minus r squared. And this is going to be dr d data. Okay, so I just substitute. I substitute z equal to 2 square root of 1 minus r squared to make it 2r. And put z equal to 0, that would be nothing. Now you have to integrate respect to the r. If you switch this one, rewrite it, then the u substitution is, it's easily done. So you rewrite it as, I go to the next page to finish it. Okay, any question? So change this one, take the inside to be u prime, you take u to be 1 minus r squared, u prime will be 2r. There is a negative sign, so we can create that one in the street. Okay, so this is how we continue. So the integral would be, I just rewrite that radical 0 to 2 pi. Okay, you have the 0, 1. Then I have the, okay, I have the 2r times 1 minus r squared to the 1/2 dr d data. So I have to use u substitution for this one. You see this is going to be u. So I like to get the du here. It's almost du, but I need a negative sign, you see. It's a du would be negative 2r dr. Okay, to make this one du, so what I can do is I can pull out the negative sign outside. So it's going to be equal to the negative 0 to 2 pi, and it's going to be 0 to 1. I call this one, negative 2r. So I can use the u substitution or just do it. So this is going to be like, u to the 1/2. Okay, you know that u to the 1/2, the u would be u to the 3/2 over the 3/2. So I do the same thing here. So it's going to be negative 0 to 2 pi. Okay, now the integral would be 1 minus r squared to the 3/2 over the 3/2. Okay, like this one over here. But r going from 0 to 1. And when you're done, you come back and you get the D there. Any question? So that's the 3/2. Switch it into the 2/3 and you can put it out. So it's going to be negative 2/3. Okay, integral from 0 to 2 pi. Then you have 1 minus r squared to the 3/2. That would be r from 0 to 1 and the data. Now substitute. If you put r equal to the 1, you are going to get the 0. Okay, r equal to 1. That give you 0. So it's equal to the negative 2/3. Okay, negative 2/3, and it's the integral from 0 to 2 pi. So we get the 0 here. Okay, you get the 0 minus, and if you put the 0, we get 1. Minus 0 minus 1. So 0 minus 1 and the d data. Okay, this negative would be 0 minus 1. Yeah, that's it. You know, we get the, because that's a 3/2. You get the, that give me 0, but yeah, that's going to be the case. So negative would be positive. So it's a 2/3 integral from 0 to 2 pi d data. Integral d data is going to be data. So there's going to be 2/3 data. And that's from 0 to 2 pi. So that gives you 2/3 times 2 pi. Okay, 4 pi third is the final answer. Okay, so the integral would be 4 pi third. Okay, it's very nice one to be able to get this one through. Okay, there is another one, but we have to wait to get to that spherical coordinate as well. Then we can compare it to see which one is going to be better. This is a cylindrical one. Any question? I can give you your break now because I want to give you a spherical one. Okay, so you can have your break one. We come back at about 12. Then I give you a spherical coordinates. We finish it. A spherical coordinates get a little bit more involved. The situation that you're going to have for the spherical one is, see, when you do the cylindrical coordinate in a kind of the two-dimensional one, you go around yourself, and data is going to be between 0 and 2 pi. So the way we do the spherical one is going to be like looking into the something. You just, you just move your neck if you like. So there is going to be another angle. We call it the declination angle. So it would be a little bit involved from the formula, but otherwise it's a nice one. Okay, so let's have a break. We come back. We could then, refresh, and then we'll be able to do it, and then we compare them together and we finish it. Okay, that's it. Let's see you then. Okay, any question? So let's do the spherical one. Okay, so that was the cylindrical one. So again, we are going to describe what is the spherical coordinate system is. Okay, then we put them together and eventually we come back to the integral. Okay, there are some integrals in triple one that you can only do it by using the spherical coordinates. And you get a chance to compare it sometimes which method is going to be easier to apply. Again, we give you the instruction to do it, but there are situation cases that you may decide yourself. Then in that case, you have the option. But on the test, if we give you the instruction, you have to follow that instruction. Okay, so that's going to be the way we're going to do it. So this is, we are on the same section. So how about a spherical coordinate? Okay, so we have to describe it first. Okay, then we go to the integral. So let's see what is going to be a spherical coordinate. Okay, that's it. A spherical coordinates. Cross section is a sphere in this case. Now, what is the situation we're going to have? You see, in the case of the spherical coordinate, we just in the case of the cylindrical one, the way we are going to we did it. Remember, in two-dimensional, the result was a polar coordinate, and we fixed the z. Now we're going to introduce a new angle again. You see, let me just remind you what we did and what this is going to be the case. You see, this is the one. So if this is going to be the x, y, and the z coordinate that we have. So so far, what we did for the cylindrical one, we pick a point. So that was the x. Okay. Then we get the y. That was the y. Then this point was the one that we call it q, which is going to be x, y, and 0. So we are into this is in xy plane. Then we move up this one up. Okay, we move it up, and that gives us the point P. Okay, the point P. So the point P, this was, this is x, y, z that we have it. Okay. So in the polar coordinate, what we did, we switch the x and the y here. Okay, we switch it and you make it to the r, and because this interpretation are crucial for the for the next part. Okay, so this is what we did, and we fixed the z over there. So in that case, these are going to be that's x, y. So we change it to we change this one into the r and the data and z. So that's a cylindrical one. Now, the way we're going to do it in this case is, you see, we get a point P, and then we are going to consider the distance of the P to the origin. Okay, this is going to be a distance of the P to the origin. Okay, so as you can see, the coordinate of this point is the x, y, z, and this is going to be the origin, which is going to be 0, 0. So a distance from this point to the origin is going to be what? It's going to be the square root of, okay, so this portion over here, this distance, usually refer to this one as a rho. Okay, that's going to be the rho, and the rho is going to be a distance of the P to the origin. X, Y, Z, you know that distance between 2 points, or distance from the origin is going to be x squared plus y squared plus z squared. Okay, so that would replace the r, if you like, in the case of this cylindrical that we're going to have. Now, what else? The other things is in two-dimensional, remember in two-dimensional, the polar coordinate, we get it here. Okay, and there was an angle here that we call it theta. Remember, this is the angle which is going to be theta. and that give you that polar coordinate we have. Now, and this portion over here, this line here, this line over here is going to be R. Okay, and you know that the R is going to be the square root of x squared plus y squared. Now we are going to bring something new. Something new is going to be this line, you see? The deviation or, of this line, if you like, from the declination, you see this it. If you compare it with the z axis over here, okay, how far it go to the right, to the left, this angle in between, okay, this angle is between, we are going to give it a name. This angle is going to be called phi. Okay, so in the polar coordinate, you already got the R, data, and Z on. Now we introduce the next new angle. This angle is going to be phi here. Okay, so now in the spherical coordinate, this point P would be identified between. We replace the R by rho. Is going to be rho. This data would be fixed as is, but we replace the Z by this angle. The angle is going to be called angle phi. Okay, that's a specific notation that we're going to have. Okay, and then we are going to find a relationship between these. So let me write it down, these expressions that we have. Okay, and we continue. So a point in a spherical, okay, a point, let's say a point P, which is the x, y, z, is going to be described. Okay, this point is going to be described in this new system in a spherical. Okay, a spherical coordinates by, okay, this is to be written, it's going to be P. Then you have a rho, just replacing the R if you like, the distance. Then we have the data. This is the angle for the polar angle. And then we have the phi, this new angle that we talk about it. Is going to be between the OP and the XZ axis. Now this phi, this rho, where we call it the radial, where the radial or distance, radial rho is going to be the distance, is the distance of P to the origin. Distance from the point P to the origin. You know that the origin is going to be 0, 0, 0, and the distance between 2 points are going to be this one. Okay, it's going to be, so the rho is the new formula, is going to be x squared plus y squared plus z squared. That is going to be the rho, the extension of the R, if you like. Okay, data is just the polar angle. Data is the polar angle. That would be the polar angle. In general, is going to be between 0 and 2 pi. Of what? Of the projection. Again, if you drop it down, project it into the two-dimensional, is going to be just a polar form. Projection of, of that point Q that I denoted for you, x, y, 0. And what is phi? Phi is a new angle. And phi is the angle between that line, okay, between rho and z-axis. Its atmos can be 180 because angle between two lines, 0 and pi. Okay, phi is the angle between rho and z-axis. Okay, you know that this is going to be z-axis and And we already introduced the row, the row over there. Now, this angle, just for your information, they call it the declination angle. So sometimes they refer to it. I just introduced this one, the angle phi is going to be called, sometimes they refer to the angle, so you must know it, the angle of, angle of declination, because, it's a deviation, if you like, from the z-axis, because it measures, it measures how much, if you like, how much rho, if you like, how much the ray, the ray through P decline, ray through P, declines, from the z-axis, from the z-axis. Okay, so this is the situation that you have. Again, data, you go around the circle, so the data in general is going to be between 0 and 2 pi. And phi is going to be the angle between two lines. So it can be between 0 and, unless you have some other restriction, but it's going to be between 0 and pi. This is the angle between two lines. Okay, it's going to be between 0 and pi. But this is going around the circle, 0 to pi. And this is going to be the case. The rho is going to be like the R, is going to be a fixed number. Then be able to take care of it. Okay, now we need the relationships. Any question? So let's go back and find a relationship between these. Okay, so I have to go to the next page and I'm going to create that. I don't have it, so I have to explain it. Okay, it's nice since you want to memorize it to know this. Okay, so, if you just check it again before memorizing. So if this is going to be again X, Y, Z in short, so the situation that we're going to have is this is going to be a point X, we get the Y, then we get the Z. So it's going to be X. Okay, then this is going to be the point B, which is going to be X, Y, Z. Okay, the situation we're going to have. I've already talked about it. This is going to be the angle. Okay, that's in polar form. So this is going to be data. Okay, and this is going to be R. This green one is R. Then what I do on the top. So on the top, we connect these two together. When we connect it together, this is going to be rho. Okay, this is going to be rho. But there is going to be angle in between. This angle is going to be phi. Okay, so I'm going to connect this one. You get the projection of the projection of this line on the x-axis. So this is going to be your z. And this R and R are going to be the same. Okay, so these two lines, if you graph it correctly, that give you the same thing. Okay, so I want to show you a couple of equations that we needed. We are going to use it for the integrations. And so look at this triangle that we have. This is the right triangle here. I'm going to take out two important equations from this relationship. You see this angle. So this angle is data. R is going to be the opposite side. You know that for the opposite side, you can go with the sine of the phi. Sine of the phi is going to be the opposite side, which is R over adjacent side. Okay. So this is one relation that I like it, or we need it. Sine of the phi. Sine of the phi is going to be R over rho. We cross multiply it, that give you R equal to rho sine of the phi. It's very important formula. You have to know it. It will help us quite a lot. Okay, then I'm would like to get the Z here. So Z is the adjacent side. So I go with the cosine of the phi. So cosine of the phi is going to be adjacent side, which is z over rho, which is the hypotenuse. So you cross multiply it, and this is another formula, z equal to the rho cosine of the phi. Okay, so we are going to use the polar form and these two together to get the relationship with the for the for the spherical coordinates. Okay, now look at this one now. Note that. Now, what do you have? In the polar form here in the xy plane, x is equal to the r cosine of it. This is the way you memorize it. X equal to the r cosine of the, but r is rho sine of the phi. So that give you rho sine of phi, okay, cosine of the data. In order to remember it, you better switch it, right? Rho cosine of the phi, sine of the psi. Cosine of that. It's like r cosine of the data that we did have for the polar coordinate. Now we change it to the rho cosine of the data. Okay? It's the same thing for the y. Y is r sine of the data. So bring the r again here. So that give you rho sine of the phi, sine of the data. You see, same thing, but I switch it, rho sine of the data, sine of the phi. Again, you see y r sine of the data, you change it to the rho sine of the data, you multiply by sine of the phi, but z is fixed. Z is new, and this is going to be r cosine of the phi. Make sure you use these correctly, the sine of the data. Okay, so basically, what we did in the case of the polar coordinate, spherical coordinate, so this is it in a spherical coordinates. So this is what we have. We have the x, y, z. Okay, in the rectangular coordinate, it's going to be changed into this format that we have. You see that's going to be the rho cosine of the data, sine of the phi. Okay, then we get the rho sine of the data, sine of the phi, but the z is fixed, is a rho cosine of the phi. So for the first two, you have the sine, but for the last one, you have the, okay, you have the cosine. This would be a spherical coordinates. Again, if you want to switch, I can rewrite it for you, but integration is going to be important. Let's write down conversion. If you want to change from one to the other side. Okay, for the conversion, if you have a spherical, so your spherical coordinate would be a rho data phi. So if this is given to you and you want to change it to the rectangular, if you want to change it to the rectangular, you need x, y, z. So you need the x, y, z. And this is the way you're going to find it. You see, just get these all together to get the numbers. Okay. What is the question? That is going to be, what is that? Should our R be a rho in our system of the equations? Oh yes, this is fine. Yeah, this is, thank you. This is a rho, you are right, thank you. Yeah, I changed this, but this is going to be exactly a rho. Yes, you are right. Okay, so I just repeat it again. So in this case, you have to find it. You have to find it, and we just repeat that system. It's going to be rho cosine of the data, sine of the phi. Okay, this is going to be the rho sine of the data, sine of the phi. And if you want to find the z, it's going to be rho cosine of the phi. So this is how you go from the, okay, you go from the spherical one to the rectangular, To coming back is like the polar coordinate that we did. Okay, then we do the conversion and the integration is going to be mostly related to the functions. That is nice to know. Okay, and the other way around, which is more important that we have to use it. Okay, the other one is you have the rectangular. If you have a rectangular, since if a x, y, z is given and you want to change it to the spherical, okay, a spherical, which is going to be rho, data, and phi. So this is the way you're going to find them. You mostly do this one. So you have to find the rho. You find the rho from this formula, x squared plus y squared plus z squared. That's your rho. For the data, you go with the polar coordinate. Tangent of the data is y over x. And for the phi, you just go with that cosine formula. Cosine of the phi. Remember, that was the adjacent side z over rho. So you mostly use this one to get through it. Okay, so that was the one. So we give a couple of examples just to get to know, just get a feeling that you understand it, and then we're starting moving on to get to the integrations. Okay, you need these three equations. So let's do one. Are you ready? So let's try. Again, you are not going to do directly this type of problem for us. So we want to find the rectangular coordinates. The first one would like you to find the rectangular. Okay, find the rectangular coordinates. Coordinates of the following. The point P is given to you. Okay, it's given to you in the spherical one, so it's going to be rho data phi. And this is it. You have a 3, pi third, and the pi 4. Remember, the order is unique. We go with the data first, then the phi. You are not going to switch it, and this is the way you are going to read it. Okay, so that's easy because you want the x, y, z. You just get your formulas. So the solution, the given information, you have okay, there you are. You have your rho equal to 3. Your data is equal to the pi third, and your phi is equal to the pi 4. So you need the x, y, z. So just get the formulas. Okay, your x is going to be a rho, like the r cosine is going to be rho cosine of the data, sine of the phi, substitute 3, cosine of the pi third times the sine of the pi 4. So that would be 3. Pi third is 60 degrees. Cosine of the pi third is 1/2. So that's going to be 3 times 1/2. And the sine of the 45 is radical 2 over 2. So we simplify together, that gives you 3 radical 2 over 4. So that would be over x. Question? Just go ahead, get the other formula. Y equal to rho sine of the data, sine of the phi. So that gives us a 3 sine of the pi third, sine of the pi 4. So that gives it 3. The sine of the pi third is the radical 3 over 2. And that's a radical 2 over 2. Okay, no decimal numbers. Okay, just give us in irrational form. So 3 radical 2 radical 3 would be radical 6. So that would be 3 radical 6. 3 radical 6 over 4. So that's your y. And the z is just brief rho cosine of the phi. Okay, the rho is equal to 3 cosine of the phi. Phi is pi 4. So it's going to be 3 times radical 2 over 2, which is 3 radical 2 over 2. Okay, that's it. So the point P in X, Y, Z coordinates are going to be 3 radical 2 over 4. Okay, 3 radical 2 over 4. And the last part, sorry, this is 6. And the last one is 3 radical 2 over 2. So that gives you the coordinate of your point. Any question? You have to do one the other way around. Just make sure you pick the, it's going to be the same problem when you go down. And the converse is not going to be unique. Then you have to check to see where the point is coming from, which quadrant, and get that one. Okay, already. Let's do one the other way around. And then we need to work for the equations as well. Okay, so the next one, convert into the rectangular coordinate. So find, or the other way around, spherical, find the spherical coordinate. Okay, spherical coordinates of this point. So the point is given in the rectangular coordinate. You see, this is given to you. So the number is going to be 2 is a negative 2 radical 3 and 3. So the point is in rectangular coordinate, and we want to change it into the spherical one. So we need to find the rho, okay, data and phi, and you got to be careful. Solution. Okay, so you want to find this one, just remind yourself, you have to find the rho, data and phi. This is it, information that you have, x is equal to 2, y is equal to the negative 2 radical 3, and the z is equal to 3. So we find the rho first, the square root of x squared plus y squared plus z squared. Okay, rho is going to be x squared plus y squared plus z squared. Substitute. So what you have is going to be 2 squared plus a negative 2 radical 3 squared plus 3 squared, 2 squared, 4. Okay, the next one is going to be, so this is 4. That's going to be 3 times 4, 12. And the 3 squared, 9, 16, and 25, which is 5. Positive, remember. So rho is going to be 5, the distance. Okay, that's a rho. The data is a polar angle. So tangent data equal to the y over x. So tangent of the data is y over x. Okay, and the y is negative 2 radical 3 and the x of 2. So that gives you negative radical 3. Now you have to locate it first and decide what are you going to do. So where is data? X is positive and the y is negative. So x positive, y negative, so you are here. So this is what you are going to pick. Okay, so the angle that you have to pick is this one. To get the radical 3. You know that the radical 3 is the tangent of the 60 degrees. So this is going to be 300 minus 60, which is 360 minus. So that give you 5 by 6. And you can get it from the table. Okay, so the data is going to be 5 by 6. Okay, so got to be careful to see where this is coming. You know that the tangent would be negative also here, but you cannot pick this one because with the information that you have, your point is on the fourth quadrant. Okay, so the data would be 5 by 6. Any question? So that's the data. You have to find the phi. So get the phi, you have to use that cosine formula. So cosine of phi, it's equal to the, the adjacent side, z over rho. So the z is simply 3, and the rho is 2. So that gives you 3/5. Okay, so the cosine of the phi would be 3/5. You can use your calculator to get this one. Okay, so the phi is going to be cosine inverse of 3/5 with your calculator, and you have something like 0.93 if you use your calculator. Okay, so eventually the point, rho, data, and phi can be identified by these numbers: 5 by third, and 0.93. You see, this is just for your information. We didn't, remember, we didn't do that, was 11.7 something, that they talk about these type of ideas, but we didn't do it because we didn't need it. But now this is the place. Okay, but the idea really, the main part is how we're going to convert the equation into the polar form. Okay, so I just give you a couple of famous one, and then we go and take the integral. Any question? So get to know this to see what is going on with these new systems that you're going to have. But your main job is this next one, conversion of the equations. You have the equation in XY coordinate, you want to integrate. So you have to change those equations into the spherical coordinate. Okay, are you ready? Let's do a couple of famous one, like the one that we did for the cylindrical coordinates. Again, in this case, you have 3 variables. You have the rho, data, and phi. So mostly you can, like in the polar coordinate, you can solve for rho if you like. So your rho is going to be a function of phi and data. So this is the type of equation that you can have. So we would be interested in finding an equation. Finding an equation of the form, okay, this form, rho equal to f of data and phi. So this is the conversion that we're going to do for us. Okay, for the given surface. Given surface or surfaces. I'll just do 2 famous ones that we're going to use. Of course, the first one is the most popular one for this integration, and that would be a sphere. Okay, that's it. It's going to be used quite a lot, and it's clear. You know that x squared plus y squared plus z squared is equal to the rho squared. So rho is 16, so rho would be 4. And always going to be used for integration, rho between 0 and 4. Because rho, remember, is a distance. It's a positive number. Okay, so that will be easy, and we do it right away when we see it. So remind ourselves that the formula is this one. Rho squared is equal to the x squared plus y squared plus z squared. In this case, it's equal to the 16. So the rho would be 4. So rho equal to the 4 is the equation of a sphere in a spherical coordinate. You see, and always rho is positive, of course. Okay, so that will help you quite a lot when you want to get the get the limit of integrations. Any question? That's the best one that you can have. If it's going to be anything else, then you are going to have an equation. Sometimes it's not going to be a nice one. And this is another famous x squared minus y squared. You know that the traces are going to be parabola. And again, you get hyperbolic one. So it's one of those, those region that we work on before, but we want just to convert it. So convert whatever you have the x, y, z, put them together and try to find the rho in terms of the data and phi. Okay, so sometimes you get something nice because of the relationship, the trigonometric identity, and sometimes you may not, but this is going to be yours. So there you are. Substitute. You substitute x equal to the rho, remember, adjacent rho, cosine of the data, sine of the phi, and you get the y, rho, sine of the data, sine of the phi, and you get z. Z is what? Rho cosine of the phi. This is the formula that you have it for this part. Okay, now nicely substitute. So it's a rho cosine of the phi. You square this one, so that gives you rho squared, cosine squared, sine square of the phi. Okay, it's minus. When it's a positive, that can be simplified quickly. So it's going to be rho squared, sine square of the phi, data and the sine square of the phi. Okay. So when these two are together, you always get this common factor, you see. This is always the case when the x and the y are involved, and you have the rho square as well. So you expect it to do the simplification, so that give a cosine of the phi, and that give a rho squared. Okay, rho squared, sine square of the phi. The leftover, it depends whether it's a difference or the sign. Most of the time it's the same, so that give you 1 right away. But this is difference, you know that cosine square minus sine square in trig, this is the cosine of the double angle. See? So remember rho is a non-zero number. In this case, you divide by rho. So you get a cosine of phi data here. And over here, you get the rho sine square of the phi. And then you get a cosine of the two data. You solve for rho. So the rho would be cosine of the data over sine square of the phi times the cosine of the two data. Okay, so these are going to be just they're going to make an identity and the operations. Again, the one that you are going to have is going to be straightforward, but you need this type of ideas just to know that how we handle it. The operation that you do when you go to the integrations, that part that you have to change the function into this new form is much, much more than the one for the cylindrical coordinates. And you will see it in a minute. Okay, so we have a new system. Now, how we're going to use it to evaluate the triple integrals. So the way we're going to do it, the domain that we have are going to be a collection of points x, y, z. We change it to this new one. When you change it to this new one, the x, y, z would be changed to the new system. The new system is going to be rho, data, and sine of the phi. So for the function part, you are going to drop these in the function like this, simplify it. But the important part is the range of the domain of the integrations, those limits of integration that we're going to have. The case is going to be, you have checked the information that we have to get this true data. You have to drop it down. You see, you get the projection in two-dimensional. When you get in two-dimensional, you'll be able to find the data, because the data is the polar angle. It's usually between 0 and 2 pi. But you may have to check, the semicircle, quarter of a circle, etc. So that's the way we handle the data. That phi is tricky. In general, the phi, remember, is angle between two lines. So it's going to be between 0 and pi. So if you don't have any specific information, it's 0 and pi. But you may be given something like z is positive, it's going to be z positive, so it's going to be between 0 and pi half. And there is one like this slice of the pizza that we did the other day for the cylindrical coordinate. That would be a tricky one that we have to do. Okay, so you need a kind of a couple of examples, but the one that involve more mathematics in the case of the spherical one is much more than the cylindrical one. So we don't usually give you a nice one, but you may see one of them on this coming test and even on the final. So be patient. Eventually it would be nice, but we know how to, because we can avoid a couple of them, but not all of them. So I'm going to give you some so that you can see how we're going to handle this. Okay, any question? So make sure you write this in order that we talk about it. Two different angles, you have to use the notation that I use. Data for the polar angle, phi for the spherical one. Okay, there you are. Since let's give you that because there's going to be extra part at the Jacobian that we talk about it. So what is triple integrals in a spherical coordinate? Okay, the general form, triple integrals in a spherical coordinate. In a spherical coordinates. There you are. We have a domain in X, Y, Z. We change it to the domain of the row of data. We put them together, and of course, there's going to be an extra part. There you are. And the way we are going to do it is this one. I just recall once, so I have this formula available. Recall that. In the spherical coordinate, have them available here. Spherical coordinates. This is the situation once more. X is equal to the rho cosine of the data, sine of the phi. Y is equal to the rho sine of the data, sine of the phi. Okay, and Z is equal to the rho cosine of the phi, because we need them. Now we have a domain, okay, we have a region in XYZ, we change it to the, okay, rho data phi. So this is it. So for a given, for a region, or the given region W, defined by what? This is it. Make sure you have enough space. W is equal to. So the coordinates are going to be, this is the way we write it down. And I write data, phi, and rho. It's the way we usually do. We do the rho first. You can switch it, of course, but this is a standard. Now, this data, that's going to be the polar angle, so it's going to be between two numbers. We call it data 1, data 2. 0 to pi most of the time. 0 pi half a circle, 0 pi half a quarter of a circle. Then this phi is an angle, it's going to be between two numbers. We call it phi 1. That's a phi and the phi 2. If everything is standard, it's going to be 0 and pi, remember. It's angle between two lines. It never is 0 to pi. So you make it 0 pi, 0, 0 pi half, etc. And then the last part is going to be the rho. Rho can be a function of these two. That's why we write it down first here. So most of the time it's going to be a number, but it's going to be between two numbers. So it's going to be rho 1 can be a function of data and phi in general. So it's going to be less than equal to the rho, and rho less than equal to the another number, rho 2, data and phi. So the way we arrange it, sometimes if the equation and relationship are not going to be straightforward, you have to find you have to convert it. You have to convert it to have the rho to be a function of data and phi. Okay, so we have the region. We change it to the spherical coordinate. Then this is what we are going to do. Then we have the integral. If you be given the triple integral 1, 2, 3, the function is f of x, y, z, dx, dy, dz. Okay, and over w. Now we switch into the spherical. So for the spherical, data going from data 1, data 2, phi going from phi 1, phi 2, and the rho going from rho 1, rho 2. Now the function. The function would be changed into the f of data phi rho. Okay. Then there's going to be extra term, Jacobian. Extra term because you just, these are all substitution method. So that extra term is this one, rho square sine of the phi. Make sure don't miss it. And maybe by tomorrow we prove it for you when we get to the next section. Okay, just make sure if this integral getting complicated, okay, you probably missed this one or you made a mistake when you write it down. Make sure that you check it. Okay, it's going to be rho square sine of the phi. And then you integrate respect to the rho first, as we write it down here. Then we integrate respect to the phi. And at the end, we integrate respect to the phi. That's it. That is the triple integral in a spherical format or a spherical form. So again, you have to shrink it, drop it down into the XY coordinate to see what's going to be the data. You will see it in a minute I do it. And that the rho part is easy. It's like the radius, it's mostly in the shape that we're going to give in. Okay. Most of the time the integral seems to be complicated, but it's not really when you put them together. Okay, are you ready? And there you are, we give you the most popular one. Then again, read this carefully. We may give you just a direct one on the test. So you have to know these examples are important examples. Okay, and of course you cannot bring these examples as I talk about it to the test as your formula share. Okay, so we want to, again, instruction was given to you. You have to follow the instruction. Use a spherical coordinate. So you have to use spherical coordinates to integrate, to evaluate, okay, each integral. They are so clear that, you have to use this, even if you don't say anything. Okay, this is it. This one is very popular, or the domain that you have. It's going to be repeated in various formats. So the first one, we want to find this triple integral. The function is e to the x squared plus y squared plus z squared dv. This integral would be given in different domains on region W. And the W is defined by this. It's a sphere where W is all the points inside and on the sphere. It's X, Y, Z, such that X squared plus Y squared plus Z squared is going to be less than equal to 1. You see, this is how we want to find the integral. You say again, as you did it for the polar coordinate, you have to take this equation that you're given. And from this equation, first thing to do, you find the rho. Then you replace the Z by 0. You drop it down in 2-dimensional. Then that should give you the idea for this, for this part that you're going to have. Okay, so this is the way you handle it. Solution, as you did it for the cylindrical one. Sometimes it would be given in the term of the limit of integration, and sometimes they describe it like this one. So a sphere is very, very popular case. So we are going to check to see what is going to be the limit of integrations. So we say, okay, we have the x squared plus y squared plus z squared less than equal to 1. Quickly we switch it, so this is going to be rho squared. Okay, so this means rho squared is less than equal to 1. Remember, rho is a positive number, so rho is going to be, okay, so we take the square root, so rho would be between 0 and 1. So this is the limit for the rho. Any question? Remember, rho is a distance. Rho squared is less than 1, that gives you the absolute value of r less than equal to 1, but since absolute value of rho, but rho is positive, so it's going to be between 0 and 1. So that's the restriction for the rho. Any question? Now, replace z by 0 to drop it down in 2-dimensional. Okay, project it into 2-dimensional. So z equal to the 0. So z equal to the 0, your result would be x squared plus y squared less than equal to 1. Now you know that in 2-dimensional, this is what? This is going to be a circle. So you're going to end up with the unit circle. You see it's going to be the unit circle. You're going around the unit circle. So in the case of unit circle in polar form, your data is between 0 and 2 pi. And there is no restriction for the phi, so phi is going to be between 0 and pi. Remember, this is an angle between two lines. One line is the z-axis, the other line is the OP, and the rho line, if you like, that the ray. So there is no restriction. So in that case, the phi is going to be between 0 and pi. So that's it. We have all the limit of integration that we need. So we can set up the integral with this limit of integrations. We have the function. We have to take care of the function. So this function, we substitute x squared plus y squared plus z squared. We substitute as a rho squared. And then we have the extra term. You'll be able to do it right away. Okay, any question? So this is how you set up the limit of integrations. So let's see how we're going to get that integral and how we're going to do it. So the given integral, I'm going to call it I. So I'm not going to repeat it. So there you are, the integral changing to the polar form. The polar form is going to be, this is it, 1, 2, 3. Okay. Now your function was e to the, you substitute for the x squared plus y squared plus z squared, you substitute going to be rho squared. Extra term is the rho squared sine of the phi. Sine of the phi, we integrate respect to the rho first, then we integrate respect to the phi, and then we respect to the data. Okay, depending on the problem, you can change the last two is going to be the same. Rho, we talk about the rho, the radius of the sphere is between 0 and 1. Phi the usual limit, 0 and pi, and the angle between two lines, and the data going around the circle, which is 0 and 2 pi. That's it. Any question? Is your integral, so this would be e to the rho, and there is a rho square over here. So it's going to be equal to the integral 0 to 2 pi, 0 to pi. Okay, so I have to take that integral first. So I have to find the integral of 0 to 1. Okay, rho squared. Okay, so sorry, yeah, it's going to be rho squared, e to the rho. Okay, then the sine of the phi, respect to the rho first. Okay, respect to the rho first. When I find it, then I come back and do the phi and the data. That's it. So this part to integrate nothing to do with the sine of the phi. Okay, so you take this one out and you start integrating. Okay, what's the question? If there is no restriction, yes, the phi is the angle between two lines. The phi is angle between two lines. You see the z-axis, this is the z-axis, and this is the rho. So in this case, you go around the circle. There is no restriction for this one. So they can be, it's going to be any angle. So between 0 and 2 pi. Sometimes you may say that, the situation is created so that you are going to be on the first quadrant only. If you are going to be between first quadrant, your phi would be between 0 and pi half. But in general, if the largest domain that you can have is going to be 0 and pi. It's like the data, 0 and 2 pi. But when it's going to be semicircle, it's going to be 0 pi. Okay, so it depends on the problem. Otherwise, if there is no restriction, 0 pi. Okay, so what we have to do, we have to find this integral first. You can forget about the sign. So I'm going to pull it out, integrate it because it takes time, 0 to 1, rho squared, e to the rho, d of the rho. You know that you have to use integration by parts, and you better use the table format that we talk about it, okay? So the table, remember, the shortcut, and this is going to be the sign. So this is, in this column you differentiate, in this column you integrate. So start with the sign positive, you put that power function here, rho squared, and this is going to be e to the rho. Then you are going to go the next part. This positive, the sign would be negative. You differentiate the rho squared would be 2 rho. You integrate e to the rho would be e to the rho. Okay, you continue. You should go down to get the 0 here. So the sign would be positive. So the derivative would be 2. But the integral of e to the rho is going to be e to the rho. Once more, this is going to be negative. The derivative would be 0, and the integral would be the same. Then you collect the information by cross multiplying. Say this is it. This is going to be the result. So what's going to be the result? Integral from 0 to 1, rho squared e to the rho d rho is going to be equal to, you multiply these two together, that give rho squared e to the rho minus, you multiply these two together, that give it 2 rho e to the rho plus, you multiply these two together, that give it 2 e to the rho. Okay, but it's going to be evaluated from 0 to 1. Okay, any question? Otherwise, if you want to go with integration by parts, it takes quite a while to do it. You know that. You have to do integration by parts 3 times to be able to do it. So a substitute, if you put p equal to 1, so p equal to 1, that give you 1e, and that give you minus 2e. Okay, and that would be plus 2e. Now minus, if you put the 0, 0, 0, and if you put here, that give you e to the 0, 2e0. Okay, but you know that e to the 0 would be 1. So these two would cancel out. So you arrive at, that's it, minus 2. Sorry, e minus. So that give you e minus 2. So that would be the integral of 0 to 1 rho square e to the rho du. Okay, that's it. So we can put it out of that integral and then you continue. Any question? So I do this part. I put it out and then I end up with the sign of the phi. So this is how we continue. Originally that was the integral. Okay, I. So now you have the 0 to 2 pi and you have the 0 to pi. So you get e to the e minus 2 times sine of the phi. Sine of the phi, d of the phi, d of the data. You continue here. Okay, you can put out that e to the e minus 2 out, that gives you 0 to 2 pi. Okay, then you find the integral from 0 to pi of the sine of the phi, d of the phi first, and then you come back, you d data. Okay, integral of a sine of the phi would be a negative cosine. So that gives you e minus 2 integral from 0 to 2 pi. Okay, then you get the negative cosine of the phi. Negative cosine of the phi when the phi is going to be from 0 to pi. Then when we're done, d data. Okay, if you substitute, that give you 2. If you substitute the phi, the cosine of the phi would be -1, negative would be positive, so that we have positive 1, and then this is 0. So this would be equal to 2. Okay, so it's going to be e to the minus -2 outside, and that would be 0 to 2 pi. Okay, 2d data. Okay, you substitute. If you put the cosine of pi -1, negative positive, that give you 1. Minus cosine of the 0 is 1. So it's going to be 1 plus 1, which is 2. Now you integrate it, that give you 2 data. So it's equal to the e minus 2 times data, 2 data. 2 data from 0 to 2 pi. You won't get anything when you put the 0, but if you put the 2 data, so that give you 4 pi. Okay, so that give you 4 pi times e minus 2, the final answer. Okay, so this is going to be the first one. Again, not difficult, but it takes time sometimes. This is very popular. You have it in different domain, different region in your book during your assignment. Some of them are straightforward, but I just picked the one. I just want to make sure that you remember this little bit of integration by parts that you may have to do it in a case of the spherical coordinate. Is very popular. Okay, any question? Ready for another one? So let's check this. In this one, the domain was described, the region, and the spherical region is very popular. So in the next one, the domain is not going to be described, but the limit of integrations directly would be given to you. Let's see how you handle this one. Okay, so let's see. I just pick the one that you may be reminded, if you like, of some formulas. So what is this integral? Look at this one. -2 to 2, that's the first one. Then -4 minus x squared to the square root of 4 minus x squared. So far that's easy because this is going to be a circle. Okay, then this part minus 4 minus x squared minus y squared. And this is going to be the square root of 4 minus x squared minus y squared. Okay, but the function, there is a function, x squared plus y squared plus z squared, and you want to integrate with this order, dz, dy, dx. That's it. So this is the one that the limit of integrations are available. So you have to put them together yourself to see what's going on for this information that you have. You can start with somewhere, you can start with this one in two-dimensional to get the situation for the phi and the data, okay? Or you can start from the last part, it doesn't matter, solution. So I'm going to look at these, okay, first. So the last integral is dx, so this means the x is between -2 and 2. The middle one is y, so that gives you the y negative. That is the middle one. And the last one, of course, is z. So it's a 4 minus x squared minus y squared, and negative, and it's going to be less than or equal to the z and less than or equal to the, okay, 4 minus x squared minus y squared. So you have to consider each equation to see that equation give you what restriction to get this true. Okay, we start from this, which is popular. So this means you have y equal to the positive, negative, the lower circle, semicircle, and the upper. Okay, then you square it. That give you 4 minus x squared. You move it, so to give you x squared plus y squared equal to 4. So this is a circle. Okay, so it's going to be a circle with a radius 2. Is the full circle -2 to 2? Okay, it's the full circle because you have a -2 and 2 here. So that's it. The full circle give you the data between 0 and 2 pi. And you have no restriction for the phi again. So the phi is going to be between 0 and pi. Okay, so that will take as true. Then we have to take care of the z. Z is here, so let's see what we have for the z. You have to find the restriction for the rho. So let's see, this will tell us what? Z is equal to the positive negative 4 minus x squared minus y squared squared. Z squared equal to 4 minus x squared minus y squared. Move them to one side. That gives x squared plus y squared plus z squared equal to 4. That's it. You know that it's a sphere. So it's going to be a sphere, and this is going to be rho squared. So that gives you rho squared equal to the 4. So rho equal to the 2. So rho is going to be between 0 and 2. That's it. It's consistent if you put z equal to the 0. Remember, if you start with the z equal to the 0 in two-dimensional, that gives you just a circle. And you already know everything is consistent. So there you are. We have the limit of integrations. There are between 0 and 2 pi, phi between 0 pi, and the rho between 0 and 2. The function is x squared plus y squared plus z squared. This function will be rho squared, and you are going to have an extra rho square sign. Then you'll be able to handle it. Okay, so now we can set up the integral. Any question? So this is, a little bit more different. The other one, the domain was described. This one is given to the limit of integrations. So let's set up the integral. That's it. The original integral, 1, 2, 3. So we do last with the data 0 to 2 pi, 0 to pi. You can switch these two last, anytime you like. But this is going to be done first, 0 to 2. Okay, your function, remember this is your function, x squared plus y squared plus z squared. So you have to replace this one by rho. It's going to be rho squared. That's going to be rho squared, extra term, Jacobian, rho squared sine of the phi. That's the one that you shouldn't miss. And then accordingly, we do the rho, we do the phi, and we do the that. You see, we shrink the integral quickly. Any question? Easy to integrate. We have the rho squared. That gives us a rho 4. So it's a 0 to 2 pi. Okay, 0 to pi, 0 to 2. Now that would be rho to the 4th. Okay, sine of the phi, d rho, d phi, d data. So we integrate this one first. So that would be root to the 5th over 5. Okay, so it's equal to the 0 to 2 pi, 0 to pi, root to the 5th over 5, and the rho going from 0 to 2. And when you're done, you do the extra part, which is going to be the sine of the phi, d of the phi, d of the data. Okay. We substitute rho equal to 2 to the 5th would be 32. And in case of the 0, we get nothing. Okay. So it's going to be equal to the 0 to 2 pi, 0 to 2 pi, and 0 to pi, 32 fifth, the function sine phi. So the sine phi, we integrate respect to this one first, okay? And the d phi and the d data. 32, you can put it out. So 32 would be out over 5, integral from 0 to 2 pi. Now, integral of the sine is going to be negative cosine. So that gives me negative cosine of the phi. But the phi going from 0 to pi. And when you're done, d data. You know that this would be 2 again, because you put the pi first. Okay, so and this is it. It's going to be 32 over 5, integral from 0 to pi. And when you substitute that, give a negative cosine of the pi. Okay, minus a negative cosine of the 0. And everything would be d data. Cosine of the pi -1, make it to positive, and that would be 1. So that make it into 2 again. So that give it 32 over 5, integral from 0 to 2 pi, 2 d data. That's it. So this integral would do 2 data, replace the data by 2 pi, so that give it 4 pi. So that would be equal to 32 fifths, okay, times the 2 data from 0 to 2 pi. For the 0, we get the nothing, okay, and then you have 2 times 2, 4. 4 times 32 would be 128. 128, okay, I write down here. It's going to be 128 pi fifth, the final answer. Okay, so that give you, again, just keep it in order, and you'll be fine to get these numbers done. Okay, so that's going to be the second one. Again, nicely put them together, the order of integrations, it would be fine to get these numbers. Okay, any question? Now, so far, so good. But if you want to see something different, it's again like the one that we did for the cylindrical coordinates. Remember, on the cylindrical coordinate, as soon as you get to the slice of the pizza or the just sector of a circle, you get quite a lot to do. There is one version of that problem in spherical coordinates. This is the only challenge that you have. Otherwise, the rest are going to be straightforward. Okay, let's see if we can do that one too. Any question? So that was the 1, 2. These are all kind of symmetric, but not this one. Give you the idea that even if you get to this type of situation, you know that you can handle it, and you know that you are expecting to do a little bit of algebra. You will see it. Okay, let's see. Let's do it. Make sure we are able to finish it. So this is going to be the one which is different. Integral from -1 to 1. Let's see what is the straight about this one. -1 minus x squared. Okay, 1 minus x squared. This is so far so good. This is semicircle, up, down, -1, 1. So 0 to pi, everything all right. But look at this. You see, this is different. That gives x squared plus y squared, and this is 1. It's kind of this is a coin. Z equal to the radical x squared plus y squared. Z equal to 1 is going to be a plane, if you like. And you're integrating between these two. And no function is like the volume problem, dz dy dx. Okay, there's no function to take care of, but it's in a spherical. If it was a cylindrical, you see this problem can be done by it's easier to do this one by cylindrical coordinate if you give in the choice. I do it for you, but you be given the instruction, remember. You've been asked to do the spherical one. That will tell you that if you pick the wrong choice, then you have to pay for it. But they usually, ask you to do it. So that's why we want to make sure you know it. But otherwise, cylindrical coordinate in a matter of seconds can be done, but not the spherical. Let's do it. Then I tell you how to do it in cylindrical too. Okay, so put them together to see what's the difficulty, what's going to be the region of the limit region that we're going to integrate. Let's check what we have. X is at the end, so the solution is going to be, so this is the X, and this is the Y. Okay, so that make it nice because it's a circle, but this is the Z. Okay, so the Z part is going to be x squared plus y squared less than equal to the Z less than equal to 1. This 1 is the difficulty. Okay. Now, this part is easy. We can take care of this one first, into dimensional, the projection. So the projection is simply, as usual, is y equal to the positive negative 1 minus x squared. So semicircle, the top bottom. So you know that we square it and then we do it. Y squared 1 minus x squared. So it's going to be x squared plus y squared equal to 1. So that's it, a circle. Okay, so I do it here because I need more space. So this is going to be a circle. Okay, so we have the circle, and the information that we can get over here is only data is going to be between 0 and 2 pi. Okay, this is the situation we're going to have. Now, you see, you cannot connect these two together directly. So that's why for the phi, you have to wait to see what's the situation, because you have to investigate this one, okay? You have to investigate it. And so the shape are going to be different. See, look at the Z. What is the restriction for the Z? So the Z is going to be, you see, these two limits are quite different. So you have to check each one of them separately, if you like. to get what is the situation we're going to have. So I'm going to check this one first, z equal to 1, because they are not popular, familiar. Z equal to 1. So let's see what it's going to be giving you. So a substitute for z. Remember the z in the spherical coordinate is what? Z is rho cosine of the phi. So rho cosine of phi is equal to 1. So then the only thing that you can get here, you solve for rho. So rho would be 1 over cosine of the phi. And you know that 1 over cosine of the phi would be secant of the phi. So this will give you the fact that the rho, you know that it's positive number all the time. So rho is going to be between 0 and secant of the data. So rho is not a fixed number because just you're having a plane here. It's like the one that we did for the circle. You see, it was a slice of the circle, a sector of a circle. So that gives a restriction for the rho between 0 and 1. But you have one more version. How about z equal to the radical x squared plus y squared? Because it's not going to be giving you the, the other part that you have, because it's the kind of area between two curves or between two regions, two solids. So we pick another one, say, oh, z is equal to the radical x squared plus y squared. So what is going to be this? What this means, if you like, to get this one. In the case of the circle, we call it r squared, but we can't do that. In this case, you have to substitute to get, if you should get the restriction for the phi going here. So that needs a little bit more algebra. So substitute in both cases. Z is rho cosine of the phi is equal to the square root of. Now bring x squared plus y squared in a spherical coordinate. Remember your x is rho. What's x? It's going to be rho cosine of the data, sine of the phi. And you need a square. Plus the y is the rho sine of the data, sine of the phi. A square. Okay, continue the algebra. Continue the algebra, square it. Just keep going. So the algebra is going to be rho squared, cosine square of the phi, and the sine square of the phi. Sorry, that's the data, this is phi. And this is going to be the rho squared, the sine square of the data. Then you have a sine square of the phi. I told you before, there's the common factor here. You see the common factor is rho squared and the sine square of the phi. So take it out. So that gives you rho squared of the sine square of the phi. So the inside, you end up with the cosine square of the sine square of the data. Sine square cosine square is equal to 1. Okay, it's going to be equal to 1. And this would be equal to the rho squared, the sine square of the phi. Okay, this is the situation we're going to have. You know that when you take the square root, rho is a positive number. So the square root gives you rho. But you have to use the square. It's going to be rho absolute value of the sine of the phi. Because the phi is between 0 and 2 pi. Okay, but between 0 and pi, because it's the angle between two lines. But between 0 and pi means you are in the first quadrant and the second one. So in that case, this is a positive number. So this is going to be equal to the rho sine of the phi. It's important, to know the reason. The reason is that, that usually the phi is between 0 and pi. So the sine of the phi is always positive. Okay. So if you put them together, so what do you have? Remember, you start with I put it over here to show you. So what I have the pi rho cosine of the phi is equal to the rho sine of the phi. So the rho and rho would cancel out. So I have a cosine of the phi equal to the sine of the phi, that angle. You can divide it if you like to get the tangent of the, so that give you a tangent of the phi is equal to 1, and this means the phi is equal to the pi 4. So for this problem, your phi is going to be between 0 and pi 4. That's it. That make it different. Okay, it's like the slice of the pizza that we did for the polar coordinate. Okay, so it's not like you have all in the first quadrant, if you like, or the second one. It's going to be a ray. That ray is going to be the angle that make it going to be pi 4. Okay, so in some of the problems you need this one, and the reason is, I told you, the reason is that your z it's a coin, z equal to the square root of x. If you graph this with your graphing calculator or the one that I gave you, then you will see it right away. Okay, so now we are ready to integrate. So how are we going to integrate? The data would be between 0 and 2 pi. Okay, that's going to be your data. 0 and 2 pi. Your 5 would be 0 pi 4. And the row, you see the row is not a number, between 0 and secant of the data. So the fun part would start now, because you substitute, then you have an integral to take care of. Okay, any question? Read this one carefully to learn this type of methods, to know it. You don't have anything other than this one, kind of not challenging, but different. Okay, let's form the integral. You see the integral is going to be a triple. So my data is between 0 and 2 pi. So the phi is between 0 and pi 4. And the rho is between 0 and secant of data, secant of phi. There's no function, so extra term is rho square sine of the phi. Okay, and simply d rho, d phi, d data. Okay, in respect to the phi, it's easy. It's a phi rho squared. Make it cubed. So 0 to 2 pi, 0 to pi 4. So it's going to be rho cube over 3. Going from 0, rho equal to the 0 to secant of the phi. And when you're done, you multiply by the sine of the phi, and then you integrate with respect to the phi and the data. Okay. Now we substitute, you can pull out the 1/3, but you don't need this third. So it's going to be 1/3, 0 to 2 pi, 0 to pi 4, 0 to pi 4, and this is going to be, you see, it's going to be secant cubed. I told you before. Secant cube is sine of the phi, d of the phi, d of the data. You see? So you want to integrate it, secant cube, secant phi, you better change it. Secant is going to be 1 over cosine, then you'll be able to handle it. So 0 to 2 pi, 0 to pi 4. So this is it. This is 1 over cosine cube of the phi times the sine of the phi. Okay, d of the phi, d of the data. So the only way you can integrate it is move this one up, use substitution. So it's going to be 1/3, 0 to 2 pi, 0 to pi 4. So you move it up, not the, okay, it's just a power, not inverse function. Sine of the phi, d of the phi, d of the data. Okay, you can take this one to be u. And this is going to be u prime, or the du. So it's like a cosine to the -3. I have to write down once more. So you can see it is a 1/3, 0 to 2 pi, 0 to pi 4. So this is going to be kind of a cosine of Okay, cosine to the -3 of the phi. Again, it's a power. It's not a inverse function. D of the 5, D of the data. Now we are ready for it. You take this one to be u, and this is going to be a du. So we're just integrating integral of u to the -3 du. You know that's going to be -2 over -2. So it's a 1/3, 0 to 2 pi. Okay, it's going to be cosine to the -2 of phi over the -2. It's going from 0 to pi 4. 0 to pi 4, then we come back and we integrate respect to that. Okay, you are going to substitute, simplify, you pull out this -2, so that gives you a -1/6 integral from 0 to 2 pi. Okay, you can bring it down. It's going to be 1 over cosine a square of the phi. Then substitute phi equal to the 0 and the phi equal to the pi 4 and the d data. Okay, substitute. So that gives you -1/6, 0 to 2 pi. If you substitute the pi 4, so that gives 1 over cosine a square of the pi 4 minus 1 over cosine a square of the 0. Cosine of the pi 4 is radical 2 over 2. So it's equal to the -1/6 integral from 0 to 2 pi. 1 over radical 2 over 2 all squared. Integral of cosine of the 0 is 1. So that gives us simply 1 minus 1 d data. Okay, you know that radical 2 over 2 would be what? It's a 2 over 4. You see radical 2 over 2 squared. It's going to be 2, 4, which is going to be 1/2. Use the reciprocal would be 2. So it's a -1/6, 0 to 2 pi, 2 minus 1. 2 minus 1, that will disappear. So that gives you -1/6 integral from 0 to 2 pi d data. Okay. So that gives you simply negative. This negative must disappear sometimes, somewhere. Can double check it the way I take it out. It's a -2. But anyway, you can check it, but seems to be all right. -1/6, because this is a positive number, 2 minus 1. So it's going to be just a -1/6 data from 0 to 2 pi. So it's going to be -2 pi 6. It's a pi third, -pi third, but I think it must be positive pi third. Just double check it to see. I can't see, but I missed over here. It seems to be fine. Probably, yeah, it's pi. It's a negative. That's going to be, that's correct. -1/3. Yeah, it should be fine, because I picked the 1/3 somewhere here. Yeah, it should be fine. So this is going to be the answer. As you can see, it's a very nice problem to be able to handle it. Just give you all the possibilities for these type of problems.
May I ask?
But yes, what's the question?
I'm so sorry to interrupt. I think I did get an extra negative, and I believe it's when you did u and du. Sine would be the du, but isn't sine the derivative of cosine negative sine?
Let's see here.
Yes.
You are
So
right.
would your
Excellent.
du be a negative sign?
Yes. So I need a negative here somewhere. That is, yeah. Thank you. So this means I have a negative here. Okay, because I have to put a negative sign here. Okay, I make a negative sign so that I get a derivative of a cosine, which is a negative sign. Excellent, thank you. It's a negative 1/3 because I know that it must be positive. So I get the negative 1/3. So this could be a positive 1/6, positive 1/6, positive, 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 pi third. Because I can prove it with the cylindrical coordinate that this is equal to the positive pi third rather than the negative one. Okay, so as you can see, this problem can be done if you just give me 2 minutes, or I mean, I can do it tomorrow if you like, but you can do it, in a few seconds with the cylindrical coordinate. This problem, you see, the difficulty was that part. In the case of the cylindrical coordinate, I do it, tomorrow. In the case of, look at this one. This is data between 0 and 2 pi. If you do with the cylindrical coordinate, you see this would be square root of r squared with just r. So that give you only what? That give you r to 1. And there is nothing here. So you're integrating 0 to 2 pi, 0 to 1, r to 1, r dz, you get it right away. But they usually ask for the spherical coordinate because you can't find this type of operation in any other problems. Okay, that's why we want to know it. Although, if you're given the choice, yes, cylindrical is much easier. I do it tomorrow, explain it for you that, you can do it the case. Okay, that's it. We have one more example. You have a kind of you have this similar one in your book. So that's why I want your assignment. But there is another one which is very popular. The region, that triple integral can be used to find the volume. So in these problems, the instruction was given to you. But sometimes you want to find the volume, another problem, then you have to use this type of methods. There is one that the solid is going to be bonded by a sphere from the top. I think the bottom one by the coin. That's a very popular problem from this section in Calculus 3. I do that one too, also tomorrow for you. And you will see them in your practice one, okay? So, and then I give you another one to show you that, how about if you want to pick the correct method? You see, you can compare all the three that we have. The three means XY coordinate directly, a cylindrical one or a spherical one, when the choice are going to be given to you. This is important. Okay, that's it. Any question? So we are almost done. We should give you one more example. We have one more interesting topics that we have to take care of, and that's kind of a substitution method. Okay, some people, they don't, for this, we call it change of variable. Some people believe that we already done the cylindrical one, a spherical one in some calculus book. They take that one as a substitution method. But we are not going to do it. We covered that section. You may be a little bit, takes a little bit time to get it, but I'll show you how you can get it. Because you did this, you can put all of these under one umbrella if you like. And that's a substitution. So it's a great section. 14.8. And we check that one tomorrow correctly. There is going to be one in between. I think the 14 point, I don't remember, 6, 7. They talk about this idea of using it for a couple of arguments in physics. I did it a couple of times, but I don't want you to lose that part of the section, chapter 15. So I do with that 15 because we are not going to lose anything. And then if you get time, I may explain it. I have it, or just post my lecture notes. You can read it for yourself. But the big section, 14.8, and we're done with the 14.8, we give it the test number 3, because that would be the end of chapter 14. We do the 15, we give you the quiz 4 and the final. That's it. Have a good one. I post the practice 1 for you. That would be 2 parts. The first part, you already done it with your quiz. I'm not going to repeat it again. So this practice 1 would cover these ideas that we did. Okay, the spherical one, cylindrical, and the area, the substitution method. Okay, have a good one and see you tomorrow. Bye-bye.